Hey, this is Van. In this video, we're going to learn to identify TLS issues caused by certificates by analyzing their packet captures in Wireshark. We will learn great techniques like exporting certs from packet captures, analyzing certificates and understanding their key components, and using Powershell to update trusted root certs in Windows. So whether you are new to networking in Wireshark and need to learn everything, or you've been doing it for a while and need to skip some stuff, I think there's going to be something for everyone in this video. If you enjoyed this video and would like to see more content like this, please subscribe to my channel. It really does help out. Server certificates are the other part of TLS that we did not talk about in the last video. So what are certificates? I'm going to simplify the explanation here to talk about their use in TLS. A server certificate is a digital credential that authenticates and encrypts communications between a server and a client over the internet. For authentication, a server cert lets us be sure that the server is who it says it is. And for encryption, the server cert encrypts data only during the initial key exchange in TLS. Then TLS takes over. On the screen, I have a certificate from Microsoft that I've exported. So what are the major components of a certificate? The subject, issued to, which is the server or website name. The issuer, you can see here it's issued by, and that is the certificate authority or CA that issued the cert. Next, we have the validity period. What is the first date it is valid? And what is the last date it's valid? And what we also see here is the public key. It's used by clients during the key exchange to encrypt data sent to the server, and the server uses its private key to decrypt this data. And lastly, we have the SAN, or Subject Alternative Name. This allows a certificate to specify additional host names, IP addresses, or domains that are valid for this cert. So how do we know that we should trust a cert? That's a good question. The answer is that we don't trust certs directly, but we trust who issued them. Each cert is issued by a certificate authority, or CA for short. A simplified definition for a CA is that they issue, store, and revoke certificates. Next question, how do we know we should trust a CA? These CAs that typically issue certs to servers or websites are called intermediate CAs. Their certificates are typically issued by root CAs, and we trust the root CAs. So getting to the root of the matter here, we trust the root CAs because there are lists of trusted root CAs from operating systems like Microsoft, Linux distributions, and Apple. Also, browsers and app vendors like Google and Mozilla, and Oracle for Java. These lists of trusted root CAs are what we trust. Now, because we trust the root CAs, we also trust any CA that they issue a certificate to, or server certs that these CAs issue. So we trust any cert issued by any CA as long as it can be traced back to a trusted root CA. I think this will make a little bit more sense when we dig a little bit deeper into certificates. So now let me show you how I exported these certificates earlier. Let's go to www.microsoft.com and look at its certificate. I'm going to click on View Site Info and select Connection is secure. And I'll click where it says certificate is valid. Then I want to click on Details and make sure Microsoft is selected, and then click on Export and add .crt to the end of the file name, and then click Save. So now I'll open that CRT file, and we can see validity, issued to, and issued by. If we click on certification path, we can see the cert, www.microsoft.com, was issued by, the one right above it, Microsoft Azure RSA TLS Issuing CA 07. That's the intermediate CA. And that cert was issued by DigiCert Global Root G2. That is the root CA. On any of these, we can click on View Certificate and see those certificates also. I have one last thing to show you here while we're talking about certificates. It's the list of trusted root CAs in Windows. So what we're going to do is we're going to go to Start and then start typing MMC and then click MMC. This is the Microsoft Management Console. So it's going to ask you, do you want to allow this app to make changes to your device? And just click Yes. So now we're going to click on File and Add Remove Snap-in, click on Certificates, and then click on Add and select Computer Account. One thing to know here, if you don't have admin access on this computer, you will not see Computer Account. So now we're going to click Next, and then we're going to click Finish. And now that you see certificates there, we're going to click OK. So expand certificates, expand trusted root certification authorities, and click on certificates. You can look through this list, and these are all the root CAs that Windows trusts by default. Now click on a certificate and look down at the bottom of this window. It should say Trusted Root Certification Authorities store contains this many certificates. If this number is, let's say, less than 400, you may not have the entire current list from Microsoft. So now that we know how certs and CAs work, let's troubleshoot some more TLS in Wireshark. But this time, we will be focusing on certificate issues. Scenario number 1. We have an internal application that's having issues. When users click on the application, they get an error message that says, server not responding. You've checked the log files, and of course, they tell you nothing. So you decide to talk to the application team, and they tell you everything looks fine on their end. They also remind you that the last time we saw this error, it was a network issue. You run an NMAP scan on the server, and the server ports that should be open are open. You don't think it's a network issue, so you get a packet capture on a PC. Before we get started, let's check one setting in Wireshark. If we're dealing with certificates like we are today, it's important to make sure we have this setting set correctly. If you go to Edit and then Preferences, expand Protocols, and go all the way down to TCP, and make sure that this setting right here, this Allow Subdissector to Reassemble TCP Streams, is checked, and then click OK. I also want to show you two things that we're going to do to prep for taking this capture. The first thing that we're going to do is an ipconfig-flushdns. So from a command prompt, I simply type ipconfig-flushdns and then hit enter. The reason that we're clearing the local DNS cache is that we want to see the DNS resolution in our capture. This will help us locate the point where our application opens and starts to communicate, but it will also make sure that DNS is pointing to the correct IP. The next thing that we want to do is mark our running capture with a ping packet. I'll briefly show you how now, but if you need more information, you can watch my video titled Wireshark Class 4.2 How to Analyze a Packet Capture TLS Encryption. The specific section in that video, the chapter is titled Marking a Running Capture with a Ping Packet. If you haven't yet seen that video, I would watch it when you finish this one. Now I've got my 500 byte ping ready here. I've got a -N1, so it'll be one ping, and I've got a -L500, so it'll be 500 bytes long. So what I'm going to do here is I'm going to start the capture. I'm going to hit enter on the 500 byte ping, then I'm immediately going to test my application, and I'm clicking on it now. As soon as the error message comes up, then I will stop the capture. So let's start with DNS. I'll type dns.qry.name contains badssl.com, since that's the domain name we're using to demonstrate in this capture. Now technically this scenario is about an internal application, so in that case we would have said contains and then our internal server name. This first packet here is where our computer sent a DNS query to find the IP of the application server. Now let's mark this packet. So I'm going to right click and mark, and I'm also going to right click and packet comments, add new comment, and I'm going to say DNS query our app. Now let's filter by ping size and find our ping packet. So here I'm going to type ICMP and data.len is greater than or equal to 500. There's our ping marking where we started our testing. I'll put in a comment here, packet comments, add new comment, that says ping 500. So now let's look at the capture with only the IP address from our DNS query. Let's put in the filter ip.addr equal 104.154.89.105. What I want to do here is add another coloring rule. So I'm going to go to View and then Coloring Rules. I'm going to click the plus sign, and for the name of the coloring rule, I'm going to put in TLS. For the filter that I want to use, I'll also put in TLS. And I'm going to click Background. What I want to do is make it just a little bit darker than a regular TCP packet, and then click OK, and then click OK again. There, that's what we want. Now the TLS traffic stands out just a little bit from our regular TCP packets. Now let's put in our TLS troubleshooting filter, and I'll also leave this filter in the description. Let's also now add our IP address. So I'm going to type and ip.addr equal, and remember this is our IP address from our DNS packet, 104.154.89.105. And then let's also add our comments. So I'm going to type or frame.comment. So what this filter says is that we want all of our TLS packets, and we want to see that IP address from our DNS query, or we want any frame that has a comment. And so now you can see here our DNS query and where we have our 500 byte ping where our testing started. We can see the TCP source port of our client hello right below where our testing started is 52280. Let's add this to our filter so that we can get this conversation only. Now to do this correctly, we need to add tcp.port equals 52280 before our frame.comment. So I'm going to add that now. So I'm going to type in and tcp.port equal 52280. So if we look at the TLS portion of that conversation, it really looks like a normal TLS exchange except for that encrypted alert. We don't see an alert level fatal protocol or any other errors like we did in the last video when we had TLS protocol version issues. It looks kind of like a good TLS connection, except we know that it's not working. So let's back out a little bit from our very filtered close view here and see the whole of this conversation with the source port of 52880. Here's something new that I haven't introduced yet, but it's a very useful command. I'll right click on this first packet, our client hello with the source port of 52280, and then I'll select follow TCP stream. A lot of the time, this first window is the best part. You can see the text of all the communications between client and server in this TCP stream. So this time when I'm looking at this, I notice the words Komodo, RSA domain validation, so I know that there are some certs in this stream. But this time we're going to close this window by clicking on the X in the upper right corner. Now let's look at our display filter. It says TCP stream equals 102. Whenever you click on follow TCP stream and then close the window, Wireshark will always change your display filter to only display that TCP stream. Sometimes this will mess you up, but this time it's exactly what we want. So let's look at the first three packets here. SYN, SYNAC, ACK. This is our three-way handshake. As we look at this, let's remember that everything that is not dark blue is not being displayed by our normal TLS troubleshooting filter. Well, now that part is going to help us solve the issue. We see our client hello, then our server hello, certificate, client key exchange, then encrypted alert. Right after that, we see that the client sends a FINAC. In simplified terms, the client is requesting a graceful shutdown of the connection. Next, we see a duplicate ACK. This means the server is retransmitting an ACK packet that it's already sent. We see a few more ACK packets, and then a packet from the server that says new session ticket, change cipher spec. So the server is just going on like everything's good, but it's not. So now let's look at the bold red packet there. That is a reset packet. The source address is the client, and reset means close the connection now. But the server's still not listening and sends a duplicate ACK packet, and then it retransmits a 312-byte packet 5 times. If we look up just a bit, we see that it's packet 5363, the new session ticket. Now remember, all of this is happening after the client sent that reset. Whenever I see a reset packet, I first check to see if it came from the client or the server. I want to know who didn't like what they saw. Also, I want to know when they sent it. Do we see any packets that say TLS application data, like this connection? Here, we do see TLS application data packets. All of them are 200 bytes or more, so we know there's a decent amount of actual data in there. Back to our current capture. Number 1, we see that the client sent the reset packet, and we notice that it happened after the server sent its cert. And we don't see any encrypted traffic, like the TLS connection was never completely set up. I'm starting to think that there's something wrong with the certificate based on what we're seeing. But since this is an internal application, we need something solid to send to the apps team. So let's prove it. I've added a few comments to the packets here in case you want to screenshot it for a later reference. So since we think it is the certificate, let's take a look at that certificate. First, I'm going to go up to the packet where the server sends the certificate. Click on it, and then go down to packet details. I click on the transport layer security fields, and then I'll click on TLS v1.2 record layer handshake protocol certificate. Then down below that, I'll click on handshake protocol certificate, and then I'll click on certificates. Now, if you look here, we see 3 certs altogether. To save these certs, right where it says certificate truncated, I'm going to right click. I'm going to go to export packet bytes. And when that window pops up, I'm going to note down where I'm saving this. And I'm going to name the file cert1.crt. The CRT extension is important because it will let Windows open the cert when you click on it. So I'm going to click enter here. I'm going to go to the next certificate where it says certificate truncated, export packet bytes, and I'm going to name this one cert2.crt. Next, I'll do the same thing with the third cert, and I'll name it cert3.crt. Now I'm going to go to the directory where I saved the certs and open them up by double-clicking on each of them. The cert1, cert2, and cert3. The first cert is issued to badssl.com. That is the cert for the actual web server. And just look at the valid from there. 4/8/2015 through 4/12/2015. Wow, it's a cert that's only valid for 4 days. Notice here that it says this certificate has expired or is not yet valid. And also notice the red X on it here. So this is our issue right here. This cert is expired. That's what was causing the generic server not responding error. So we know that the actual server cert is expired, but let's look at the rest of the certs in its path to a trusted root. I'm going to click on certification path. Its intermediate cert looks good. And also notice that the intermediate cert is here, cert number 2. And we also see on both of these that the root cert is named Sectigo formerly Komodo CA. And again, Windows is not displaying a red X. So that cert is in our trusted root store, and therefore we trust it. If we look at the cert on the right here, cert number 3 that the web server sent to us, it's valid only until 5/30/2020. So it looks like it's an old cert for that same intermediate CA. If we click on cert path on this one, we can see 2 red X's. So this certificate and its root cert are both expired. We also want the apps team to get rid of this old expired cert. It's not the root of our problems here, but it can only cause problems later. So now that we know the problem, we send the cert1.crt file over to the apps team, along with the commented pcap, so they can see that the cert is bad, and they fix the issue by getting a new cert issued. And they also get rid of the old expired cert. Just a quick security tip here. I sometimes see companies training users just to click through cert errors for internal web applications, rather than fixing certificates. This is not a good security practice. If the users get used to clicking on bad certificates like that, they're going to click on something from bad guys, like these two.
Hey, don't listen to him. Teach him to click on everything. Yeah, and use default passwords too. We like looking at your data.
Scenario number 2. Okay, one more scenario, and I'm going to speed this one up since it's a lot like the last one. You have a desktop app that's working fine for 5 people, but not working at all for 2 people. They are getting a connection error as soon as the app loads. You call the app vendor and they say it's your issue. Probably it's your firewall blocking the traffic. Since there are only 2 people having the issue, you start to believe them. But this problem is saying computer to you. So you get on one of the computers that's not working and take a packet capture. You mark that pcap with a ping and find out where it's failing. Then you look at the TLS with the TLS troubleshooting filter, and sure enough, you see an encrypted alert. You zoom in on one particular conversation by right-clicking a TLS packet and then clicking Follow TCP Stream. See the client reset and export the certs. When you look at the certs, you see that one of them says untrusted root. But this is a normal app that should be working, and the name on the root cert looks normal, like it should be a trusted one. Now, back to normal speed. So we have 2 computers not working, and the computer we're on is complaining that the Komodo RSA CA root is not a trusted root CA. So we go to the Windows button here and type MMC and hit enter. Say yes, we want to allow it to make changes. Remember that you need to be admin to see your local trusted root certs. Okay, we're going to click on File, Add Remove Snap-in. We're going to go to Certificates and click Add. Select Computer Account, then hit Next. Local computer, Finish. Click OK. Then we're going to expand certificates, expand trusted root certification authority, and then click on certificates. Now, if we look at the bottom of the window here, it shows the total trusted root certification authorities that we have in our local computer trusted root CA store. If that number is not somewhere around 400, then we've got a problem. If we look here, we can see that we've got 87. And then if we look up here where the Komodo RSA certification authority should be, it's not there. So it's really not a trusted root CA as far as our computer is concerned. What we need to do is update the list of trusted root CAs from Microsoft. Normally when I see this issue, it's a new computer, but it can happen on existing ones too. So go to the Windows button and start typing PowerShell and then click on Run as Administrator. A word of caution here. Even though this is a simple process that I've done many times without issue, there's always a risk. It's always a good idea to make sure data is backed up first. A safer way would be to run Windows Update and let it do this for you, but that is not always an option. The first thing we're going to do here with PowerShell open is to type cd /temp. If you didn't have a temp directory, then you would type md /temp. I get an error here though, because I already have the temp directory. What we're going to do first is grab this first certutil command and copy and paste it. What this did is it went out to Windows Update and grabbed the current list of the trusted root certs and added them to a roots.sst file. We're going to grab this second command here, copy and paste it, and this one is going to add that roots.sst file to an SST store variable. Hit enter there. Finally, we're going to grab this last command and copy and paste it. This command is what actually updates our trusted root certificate store with the information in the roots.sst file that we downloaded with the certutil command. As you can see, all the certs will kind of fly by on the screen there. So now let's open up MMC again and see how many root certificates we have. Click on Add Remove Snap-in, then Certificates. Remember, we're going to select Computer Account, then Local Computer, and hit Finish. And then OK. So expand Certificates, expand Trusted Root Certification Authorities, and then click on Certificates. And if you can see down here at the bottom of the screen, we now have 490 Trusted Root CAs. And let's look for that Komodo cert now. There it is. the Komodo RSA Certification Authority. So we went from 88 trusted root certs to 490. The number can vary depending on what version of Windows you have, but 490 looks good. We try the app again on the computer and it's working. Updating the root certs fixed it. So our connection error message from the app was really not very accurate. Unfortunately, a generic error message like this is frequently all we get from the application. So many times, it's up to us to take a packet capture and really see what's going on. Because if we're not looking at the packets, we're really just guessing. Hey, this is Van. Thanks again for watching. I know this one was a little longer, but I think there was some really good information in this video. So I'll see you again at the next video.